Okay, welcome to this lesson. We're going to be talking about a new concept here, simple harmonic motion. Now it links very neatly together with that work which might have been done previously on circular motion. And hopefully in this lesson today I will draw the links between those two. Let me first of all, let's try and characterize what is simple harmonic motion, or often called SHM. It's a vibration of sort which is characterized very specifically. But let's see if we can try and put some types of vibrations into the category of SHM, or what I'll just call another vibrations. Vibrations mean, of course, that it's vibrating around a midpoint, around an equilibrium. So let's look at the first one. What about if we have a pendulum that's being suspended from a position on the roof or a ceiling, and it's swinging back and forth? Is that SHM or not? Well, there's no good reason why you should know without me justifying it, but let's just put some into these categories and then we'll explain why these are afterwards. This is SHM. It's isosynchronous, it's always having the same time period, so I hope you realise that. So time period is constant, which is other factors unaffecting the maths and so on and so forth. But actually, most importantly, the amplitude does not affect the time period. Now that's quite critical and quite characteristic of all simple harmonic oscillators. Here's another one I hope you can imagine. What about a spring with a mass at the bottom? It's displaced, and then what happens to it? I mean, the question you should ask yourself first of all, I suppose, is does the time period here depend upon the amplitude or not? And the answer is, again, no, it doesn't. Time period does not depend on the amplitude. It's, again, mass on a spring. It's simple harmonic motion. Okay. What about an air track? I don't know whether you've seen them. Air is pushed through a series of holes and a glider sits on the top. And then usually at both ends there's some sort of elastic which then the glider bumps into. And between these points, the velocity is zero. So it bounces back and forth. Now, in this case, though the time period might seem the same, and we can't make the argument about the amplitude, this is not SHM. This is, so we put glider on air track. Okay, and let's take a look at one more example. What happens if I had a U-bend of water and I displace the water a little bit higher at one end than the other? What would happen there? Well, we know it's going to bounce back and forth when it's released. So this will drop, but this will rise, and then as it goes through its equilibrium position, should I mention that there, it will subsequently go through the equilibrium position, but then we're going to have it heavier on this side than that side, and it's going to come back down again. That is indeed SHM. So we call this U-bend of water. Now, what is it that makes three of these SHM and yet the fourth one not? Well, what we need to understand with simple harmonic motion is the definition. I'll just hit you straight with the definition. Is that the acceleration is directly proportional to the displacement. And directed towards the equilibrium. Position. In other words, if I was to write it mathematically, the acceleration is directly proportional to displacement and directed towards the equilibrium position. That is my definition for simple harmonic motion. However, I never find accelerations easy or intuitive to understand, so what I do instead is I say to myself, well, F equals ma. So therefore, what I should be saying to myself is the force directly proportional to the displacement and directed back towards its equilibrium position. So this is what I do to see whether that works. So I'm going to think to myself, well, where is my resultant force? And actually, if that's a resultant force, let me be absolutely technically correct, put an R there. Where is the resultant force on all of these objects first? So let me draw this in blue. Let's go back to the original one here. Let's go back to an easy one that we know. This is my force, a resultant force. And I know that there is mg working here, but that mg and fr equal each other at an equilibrium position. So if I moved a little bit further than the equilibrium position, then the restoring force is going to equal to the spring constant times by x. I don't know whether you remember that from Hooke's law, but nonetheless, that's what's going to restore it. The further this moves down, the greater x, the greater the force. This is directly proportional. And also, it's restoring, it's forcing it back. Let me draw this in red. This is my restoring force. It's returning it to each equilibrium position. So I'd say, yes, that is simple harmonic motion. It agrees with what I'm saying. And therefore, for the perfect definition, acceleration must therefore be proportional to the displacement and returning itself to there. What happens with the glider? Well, yes, there is a force here, and there's a resultant force there, but in between, there must be, the resultant force is zero in order to have constant velocity. Newton's first law. So therefore, it's not directly proportional. We can't argue that it's directly proportional, because we know it's for a long period of time it's going to be zero. Then you have a big force here, then it's going to be zero. Then a big force there, and then it's going to be zero. So that's why it sits on this side. What about the U-bend? Well, in this position, there is a downward force, a resultant downward force, in actual fact. I should probably draw that in red. And the bigger the displacement, the bigger the restoring force. I think if you have remembered, pressure is rho g h, h being the sort of the distance between these two. And of course, you know pressure is a force over an area, so that's rho g h. So you can here say that the force is proportional to the displacement, height in effect, and we know that it's forcing itself towards the equilibrium. So therefore we can say the acceleration is proportional to the displacement. Again, tick, tick. That's why it's sitting on that side for simple harmonic motion. So that's how I would always think about things. What's the resultant force? Does that resultant force grow and diminish according to the displacement from the equilibrium position? And is it restoring it towards the equilibrium position? If your answer is yes, then it can be inferred that it's a simple harmonic oscillator. Please remember this description, not this one, but use this in your brain. Now, mathematically, we've talked about things. What does that look like mathematically as well? Because you might be offered this type of graph. Now, very simply, that indicates simple harmonic motion. It is y equals x, inverted, as this is. But do memorize these. Good. Now, let's just show you that as an animation, because I managed to download a wonderful animation here. I'm actually going to show you where I downloaded it from, that being a great website. I'm just trying to find the picture here. and that being a wonderful website, which is it's salford.ac.uk. It's University of Salford, Manchester. Hope you can see that there. I've taken a large number of animations from there, so hopefully given it the credit that it deserves. I'll put it in large for you there. And this is the acoustics bit of Salford. That's the thing. So I'm going to leave that there for credit. Give credit where credit's due. And I'm going to find for you, hopefully, a video of a nice, simple harmonic oscillator. Here we are. So there are our simple harmonic oscillators. Now, I said before that it doesn't matter about the amplitude of these oscillations, whether that's very far from here or down there, that the time period is the same. How do we alter the time period is a fair question, and though this will be looked into much more depth later, I want to give you a feel for how that might be done intuitively in the first instance. I'm going to find you another animation from the same excellent website. Here it comes. And what we're doing here, before I kick this off, is we have an ability to change the size of this mass from light, medium, and heavy. I want you to see what happens. Okay, so my cursor's going over and I'm going to select these different sizes in a minute. The green shows the resultant force, and you can see the resultant force building the further away it's moving from its equilibrium position. Now it's moving faster, and when it's more, it's working incredibly fast. And you might say to yourself, you might wonder if that makes intuitive sense. Well, let's have a look at it. Let's have a think. What we noticed was the acceleration was growing, and the acceleration is going to be the force divided by the mass. Now, for the same given force, if the mass here decreases, then therefore the acceleration is going to increase. So you can see a greater acceleration. That in turn changes the time period. So the time period increases when the mass increases, and vice versa. Good. Just to bear in mind, so intuitively you've got an idea of what happens when the mass changes from small, medium to large. But we'll deal with it, whether that's directly proportional relationship or not, we'll deal with it with the maths a little later on. Good. Let's start a new slide and look at the next animation, where I'm going to try and draw together an appreciation of how simple harmonic motion and circular motion come together. I'm going to put this one down there for the meantime and get you just my next one, which is here. Perfect. Now, so let's juggling around a bit too much. So this is how circular motion and SHM come together. Now what we've got here is we have this rotating object. You can imagine the tip there, the red tip there is going around in a circle quite nicely. Let's watch it go around. Now I'm just going to pause it there briefly, because what's now happening is we're projecting this, and that's what we know is circular motion. We're turning the disc slightly until it gets to this position, and then we're turning it until it's completely side on, so you're going through those three positions. And what you'll notice is, as it goes, that what is circular motion on this side, slightly circular, is turning into, it's got ahead of me here, is turning into simple harmonic oscillation motion when it comes to the side view of the disc. Let me show you one more time. Excellent. And therefore that brings me to the next one, therefore, which is going to do that in just a little bit more detail. Just get to the right screen. straight enough? Pretty straight. Sorry for all the movement. Good. Now I've started it here, and we can see this is a simple harmonic motion. And whilst I've got time to describe it, whereas this has a nice even radial velocity, you can see this one builds up its speed. It goes fastest through the middle, and then it slows up until it's at 0 speed, and then it will speed up again and go through its fastest point through the equilibrium and slow up until it's hit 0 speed at the edges. So some ideas to bear in mind, that being that at the point here where we've hit an amplitude, i.e. max displacement, that's also where the velocity is 0. The acceleration, on the other hand, that's interesting, because what we've got going on is, if it's slowing up as it's moving this way, then that must mean the acceleration is pointing in that direction. And similarly, as it's slowing up as it moves along here, the acceleration must be in that position. In actual fact, the acceleration is at a minus max at the very top, and the acceleration in the middle equals 0. Though the velocity is at a max in the middle, and the amplitude, well, there's no amplitude here. Should I say, sorry, I've sort of been confusing that. The displacement x is, and when x equals 0, that's a bit better. Oops, I'm sorry for that. So we have one condition of when it's at its maximum point, when it's going through the middle, and of course the reverse of this when we're going through the other point. Now that will be useful when we start to devise the maths around this and understanding what's going on with the maths. So if we've got an appreciation of what simple harmonic motion is, let's come back up to the top and have a look at how that might be traced out. Now what we have here is we're imagining the time and the displacement. We've got this wonderful sine curve, or it could be sine, it could be cos, but we've got a trigonometrical relationship going on here. We're going from a maximum point to a minimum point with a nice constant time period. Now, let me just pause there. Oh, let me trace it out one more time for you, so you can just see that and what's going on. Oops. Excellent. Now, we need to deal with the maths of a simple harmonic oscillator. And you can see from this already, let's try and guess at what we've got going on here. You can see here that I've got a nice either a sine or a cosine wave. It has, obviously, as well, it's going through a time period. And if you remember to yourself, the time periods dictate a, dictate a frequency or an angular speed at which is going round. So 2 pi over t gives me my angular speed, how fast it's moving, which in turn gives me 2 pi f. So if I want to know how many angles I've gone round here, the number of angles I've gone around are going to be omega t. So we're looking at a sine or cos of omega t. And I know that sine varies between -1 and 1, and so does cosine. But of course I'm looking for an amplitude there. So really it will be amplitude times by this function. So I've got an amplitude stuck in there as well. And this gives me x so far. And then I want to try and resolve this issue. Well, I know that sine of 90 gives me 1. But I know that cos of 0 gives me 1. I also know that if this is my sine function, let me just write the sine function, this is my cosine function, I can see that one just lags the other. In actual fact, I hope you know, I'm sure I've explained it very badly, that one lags the other by pi over 2. They are 90 degrees out of phase to one another. It's a phase shift of 90 degrees. Now it depends which way we look at this, but whether it's one way or the other way. But so you can start from either. If this is a cosine, it's 90, and cosine is the other way around. So essentially what I'm trying to do here basically is take that for you and go, okay, well let's resolve, let's go with it. We know that it's an amplitude. Let's go with cosine omega t, and therefore we need to include this phase change. And there I have a completed expression for the wave that you see here. So without doing too much, or without just throwing that in, hopefully you've seen how we've generated it and used your intuitive knowledge of how we've generated it. Okay, let's jump to a new slide and see how that comes together. So I can jump straight in now and say that x, it's a cosine omega t minus, and we use eta as my expression. Okay, now what we did before was that we said that, I'm going to leave this at the top here, we said that the acceleration is proportional to minus the displacement. Or indeed, in order to replace that proportionality, I'm just going to put in a constant. Let's call it k. Put that up there. So that defines SHM. Okay. If we want to move from acceleration to velocity, then how do I do that mathematically? Well, if I take the first derivative with respect to time of my displacement, I get my velocity. If I want to move to acceleration, then I have to take first derivative of velocity with respect to time, which in turn is the second derivative of displacement with respect to time, squared. I wonder how good your maths is. What happens when you differentiate cosine? You get, if you can remember, it's a minus sign. So, and also whatever is inside this bracket becomes multiplied out. So therefore I'll find myself with a minus omega a sine omega t minus eta. And if I did that again, I'd come out with minus, because sine now becomes cosine, no change in value, minus omega squared a cosine omega t minus eta. Indeed, what I've got here is minus omega. Hold on, sorry, wait. Indeed, what I got in this next one is minus omega squared x, because all of this here is merely x. So what I've effectively written, if you look at the two edges on one side and the other side, is I've got the acceleration is minus omega squared x. The constant of this simple harmonic motion is omega squared. Now, please remember these three equations. It's very important. And some consequences. Those being, what's the maximum velocity that you're going to find? Well, if I write out minus omega a cosine omega t minus eta, when I want this to be a maximum function, the maximum function occurs when cosine is 1. And if cosine is a 1, then I get minus omega a. Remember that. What about acceleration max? Well, in a similar way, we've got minus omega squared a sine omega t minus eta. When this function is 1, I've hit a maximum, which is, oh, sorry about that, it's just jumped, which means I've got minus omega squared a for the maximum acceleration. Now, a little bit tougher, but another derivation that you shouldn't be unfamiliar with or unconfident with. What's the expression for v? Well, when we get to v, we need to be a little bit careful and appreciate another trigonometric identity. And that being, we have minus omega a sine omega t minus eta. Now let's imagine the etas are 0, so there's no real phase difference. So we're trying to simplify this because it's going to get quite mathematically busy. So this is my phase is 0. And we also know that sine of omega t is the same as the square root of 1 minus cosine squared of omega t. Now I'll tell you why. It's because the identity, the trig identity, sine squared theta plus cos squared theta, is 1 in all cases. Now what's my expression for cos omega t? Well, I'll put this in blue. If I know that a cos omega t is going to equal my x, and x squared is a squared cos squared omega t, then if I was to substitute into here, sine omega t equals the square root of 1 minus x squared divided by a squared, which I hope you can see I've divided through by a and I've substituted into there. Now let's roll that back out again, and I have v therefore equals minus omega a 1 minus x squared over a squared. Tidy up a bit, that becomes minus omega a square root of a squared minus x squared over a squared. You know, those two cancel out. That gives me v is going to be minus omega square root of a squared minus x squared. Quick check, I said that v max is when the displacement equals 0 as it moves through its equilibrium position. Well, that would be minus omega root a squared plus minus 0 squared, giving me minus omega a tick. So again, please use and appreciate that. Okay, now, last point. I think I need to write down those equations all over again. Let's hope this is not too luminous. X is equal to a cosine omega t minus eta v dx by dt minus omega a sine omega t minus eta, and acceleration is d2x by dt squared minus omega squared a cos omega t minus eta. Now this could easily be sine omega t minus eta plus eta, because I just invert that round. So bearing in mind it doesn't really matter whether it's sine or cosine, so long as I've got this bit to move me along my graph. But I think that's the point. The graphs are the interesting bit here. So what does dx by dt actually mean? Well, that's the gradient. And what is, and I know that my second derivative of displacement is my acceleration, but also my acceleration is the first derivative of velocity. So this one is the gradient of the previous one. Now that, you might think to yourself, what on earth is he on about? But let's just take a look at the graphs. Because what do we have here? Oh, sorry for the shaking. But here is, in effect, my A cosine omega t minus eta. And I know it starts, the displacement starts here, which suggests that actually that should be sine. So what I'm going to do is just draw my own line here of saying this is where the displacement starts. So you can ignore that. And this is where the velocity starts, and this is where the acceleration starts. So ignore those ones, ignore those lines. And so therefore blue would make sense that, and I could write this confidently, it would be A sine, or should I say minus omega A omega t minus eta, which is right, because if this was a positive sign, then it would be doing that, but this is a negative sign. And therefore finally, for my green, minus omega squared A cos omega t minus eta, which again is right because I've got minus cosine, which is inverted right down to here compared to that one. At any point, let's imagine I take this point here. Oops, that's a terrible line, but the gradient is maximum negative, which is that point there. Good. The gradient is 0. The gradient here is max positive. 0, maximum positive. The gradient here is 0, which is perfect there. This is a maximum positive, which is that point there. This is a maximum negative. Sorry, the previous one. That's 0, hence that's there. So I hope you can see how these graphs, here, are exactly those equations. And of course this is how it's all put together. Okay, I think it's time for probably some questions on this, the mathematical questions on this, so we can see how those equations are put together. Now, what I want to do is I want to show you a graph of a wave and try and give that wave the equation in the form that we've just been talking about. Here is the wave. You'll notice that it is slightly offset for a reason. I've tried to draw it as well as possible. Failed miserably, but here we go. 2 millimeters minus 2 millimeters is what it oscillates between. I know that this is running at 12 seconds, 26 seconds, 40 seconds. I'm going to tell you that's 33 because I've drawn it so badly, and that is 5. Now, what we want to do is we want to write the equation, write it in the form that we talked about before, A cos omega t minus eta. Now, you might think you'll be able to place in the necessary values for each of these, which you might be able to. So, well, let me just give you one more little hint, and then I'll let you try it yourselves. Omega is 2 pi over 2 is omega. So hit pause, give it a go. If you Would prefer, though, let me guide you through the solution. Now, we know that the amplitude is the maximum displacement, which is 2 millimeters. We know also that the time period is the point between 2 points which provide the smallest repeating unit in that wave. It's going to be 33 minus 5, which is 28 seconds. I should have just said that's t in seconds. And this is x in millimeters. Okay, now, therefore, we've got 2 pi over 28. Good, let's write that down. 2 cos 2 pi over 28, t minus eta is x. Now what I could do is take a sort of a stab and a guess as to what sort of phase this is all shifted by, because in effect, what's happened is my axis that would sit there has now been moved backwards, so it's sitting there, or my start point is slightly off, so I don't start at the maximum, I'm starting somewhere behind. So all I've done is I've shifted it that proportion of an entire quantity. So what I could just say is that, shortcut, watch out, I could just say that I've shifted it 5 seconds of what I know is 28 seconds. But I'm not going to do it that way. What I'll do, bulletproof, is by substitution. So what I do know is I know that at 5 seconds, x equals 2 millimeters. And let's substitute that in. 2 equals 2 cos 2 pi over 28 by 5 minus eta. These cancel to be 1. So cos of this function must equal 1. So when does cos of something equal 1? Well, when cos is at 0, when cos is at 2 pi, because it's 0 or 2 pi, not at pi because that's minus 1, we're talking about 1 positive, so it's 0 or 2 pi. So let's go with the opposite of 2 pi. So all of this needs to equal 2 pi. Let's work that through then. So 2 pi times 5 over 28 minus eta is 2 pi. Therefore, 2 pi, open brackets, 5 over 28 minus 1 equals eta, which equals, once I've substituted it all in, gives me something order of minus 1.12 radians. So therefore, to finish off in blue, x is a cos, and I will even bring down the 2 pi times 5 over 28, which is 0.22t minus 1.12. There it is. I hope that makes sense. Now the next problem talks about a pendulum. Now I haven't talked about the pendulum and the rationale for the pendulum, but we do know it swings back and forth. And so therefore we do know it's going to present some sort of sinusoidal wave. And what it says here is that the pendulum bob is set to oscillate by applying a nudge to give it a speed of 10 from the subsequent starting position. So let me set this up. It's actually a problem taken from the textbook. That being that initially it's here, and then it's given a nudge of 10 meters per second. So what we could say is initially we're sitting at 0, and then we're oscillating. Good. But we do know that that equals V max, because at the bottom it's given the nudge of 10 meters per second. And the time period of the subsequent oscillations is 1.5 seconds. Now part A says, express x as a cos omega t plus eta for all subsequent oscillations. So if you think you know how that's done, hit pause, Otherwise, I'm going to show you the answer. Well, interestingly, how do we work that out? Well, we know that V max is going to be omega A. We also know, and I suppose I got a bit confused there, hold on, let me backtrack a little bit. We know that omega is 2 pi over t. So 2 pi over 1.5 gives us, let me think how much that's going to give us. 2 pi over 1.5 gives us 4.19 rads per second. Now, bringing these two together, therefore, says that V max over omega is the amplitude, which is 10 over 4.19, gives us the amplitude, gives us the speed, which is 2.39 amplitude meters. Now finally, we know that at t equals 0, the x equals 0. So therefore, 0 equals A. Let's substitute A. Well, let's just leave it actually. Omega t plus eta. And we know that omega is 4.9, so that's probably what we want to change here. We've got 4.19 t plus eta. Now, when does cos of a function equal 0? Well, cos of a function equals 0 when cos of theta equals 0, when theta equals pi over 2 or 3 pi over 2. Well, which one are we going to choose from this? Well, do we have any hints? Well, we know that, well, let's just plug one of them in, because our solution should come out okay. So therefore, we have 4.19, our time period is 0, plus eta must equal pi over 2. Straightforward. And so therefore, I was overcomplicating that again. So therefore, our equation is x equals 2.39 cos 4.19 t minus pi over 2. Okay. Now we have the expression. The question asks, part 2 asks, what is the position, velocity and acceleration when t equals 1 second? So here we go, just lots of crunching of numbers here, but if you think you're ready for the challenge, go for it on your own. Otherwise, here comes the answer. So x is going to be 2.39 cos 4.19 times 1 minus pi over 2, which gives us v is going to equal minus 2.39 by 4.19 sine 4.19 minus pi over 2, and acceleration is minus 2.39 by 4.19 squared cosine 4.19 times 1 minus pi over 2, and that gives us a series of answers of what is 2.1 minus 5.0 and 36. Good. So if you, hopefully you've crunched the numbers and come to the similar conclusion. Okay, last problem now, before I leave you on your own. And that says, a person standing on the Millennium Bridge. Again, this is taken from the textbook. and found herself to oscillate with the amplitude of, so we've got an amplitude of 7.5 millimeters and a period of 1 hertz, 1.0 hertz. First bit says, what's Vmax and Amax? If you think you know, hit pause, otherwise here comes the solution. Well, time period of oscillation t equals, well, that's a bit misleading because it should be more like the frequency. And we know that 2 pi f equals omega. So therefore omega is 2 pi. Vmax is omega a, which gives us 2 pi by 7.5, which gives us our answer, which is in the order of 0.047. Was that millimeters per second? Now, omega squared a gives us 2 pi squared by 7.5 gives us 0.3 meters per second. Now, something I've just suddenly realised, that's why I went calm a little bit. Okay. I should really have this as times 10 to the minus 3 times 10 to the minus 3 equals. Right, there we go. Better. B says a position t equals 0, x was 5 millimeters. It's meant to be a 5. Velocity was negative, and express x in terms of a cos omega t plus eta. Well, how do we go about this? Hopefully it's straightforward. Well, if we say to ourselves that we know what omega is now, we know what the amplitude is, so let's write this in, 7.5 cos of 2 pi t plus eta, then let's substitute. At t equals 0, we know that x equals 5. So therefore, 5 is 7.5 cos 2 pi times 0 plus eta. 5 over 7 plus 5 cosine to the minus 1 gives us eta, which gives us about 0.84 radians. So therefore our final expression is x is 7.5 cos 2 pi t minus 0.84 radians. Okay, I hope that makes sense. Next time we'll deal with more of the physical solutions to mass on a spring, pendulum, etc., etc.